So here, this would be the free body diagram on the left for the system here. And then for part A, they want us to find the Young's modulus. So we can say that the Young's modulus is going to be equal to the stress divided by the strain. And we know that the stress is going to be equal to the force divided by the area. So in this case, it would be the tension force divided by the area. And then this would be over strain. So it'd be the tension multiplied by the original length divided by the change in length. And this is going to give us the Young's modulus equaling, for the area, it would be pi times the diameter squared divided by 4. So we can say that pi d squared. And then on the top, we can have a 4. And then we can say that, furthermore, the tension force is simply going to be mg. And then times the length. And then here it would be divided by 4.22 times 10 to the negative 4th meters per kilogram times the mass. So because it's per kilogram, we have to multiply it by a mass, and this mass cancels out with this. So essentially, for the mass divided by the change in length term, we can simply substitute 4.22 times 10 to the negative 4th meters per kilogram, and then cancel out mass in the numerator. With that, we can then solve and say that the Young's modulus is going to be equal to pi times the diameter squared, so 8.6 times 10 to the negative 4th meters squared times 4.22 times 10 to the negative 4th meters per kilogram. And then for the numerator, it'll simply be 4 times the acceleration due to gravity, 4.8, we'll use 9.8 meters per second, and then times the length of 22 meters. And we find that the Young's modulus is going to be equal to 8.7 times 10 to the 11th pascals. So this would be your answer for part A. For part B, they want the radial acceleration and the velocity, and then finally, again, the change in length. So we're going to first have to say, in order to find the velocity so that we could find the radial acceleration, we can say that the potential energy is going to be equal to the kinetic energy. So this would be the law of conservation of energy. And we can say that in the beginning, there's only gravitational potential energy. So we can say that mass times gravity times the length minus mass times gravity times the length cosine of theta, so the difference in height, essentially. And then this would be equal to, of course, half mv squared. We can cancel out the mass. And we know that v is going to be equal to 2gl times 1 minus cosine of theta to the 1/2 power. And essentially, at this point, we can solve and say that v equals 2 times 9.8 meters per second squared times 9.5 meters, the original length, 1 minus cosine of 36 degrees, all to the 1/2 power. And we find that v is equal to 9.51 meters per second. Now, once we have this, we can say, okay, the radial acceleration we know to be v squared over r. So let's solve this. We can say 9.51 squared divided by 22 meters, the radius, and this is equaling 4.11 meters per second squared. So at this point, we can find the magnitude of the tension force by saying that sigma F in the y equals the mass times the radial acceleration, and this will be equal to the tension force minus the weight, so a mass times gravity. And then we can say that tension is simply going to be equal to the mass times the radial acceleration plus gravity. So this is going to be 9.5 kilograms times 9.8 plus 4.11, and we find that the tension force is going to be equal to 132 newtons. Now, from the this would be the tension force, and this is extremely important in order to find the change in length. So we can say that these are just key values, they're not the answer. From part A, we know that the Young's modulus equals the tension times the original length divided by the area times the change in length. So we can say that the change in length simply equals the tension force times the original length divided by the area times the Young's modulus. So at this point, we can solve and say that this is going to be equal to again pi times 8.6 times 10 to the negative fourth meters squared times 8.7 times 10 to the 11th pascals. And then we'll have 129 newtons times 22 meters. And so the delta L is going to be equal to 5.54 times 10 to the negative third meters. So this would be the change in length. This would be your answer for part B. That is the end of the solution. Thank you for watching.